I've been thinking for the last few days about modeling the brain and how the brain works. And I mean, we've obviously learned a lot for AI, cognitive science, and other disciplines. We've learned a lot from trying to model the brain. I mean, the neural networks that are having so much success in AI today are loosely modeled on aspects of what's going on inside our heads right now. That said, I think neural network models, as people are playing with them now, are incredibly bad models of the brain, and they miss an awful lot of what makes the brain interesting. Now, I don't think we really need to model our AGI systems on the brain. I mean, the Hyperon system that I'm spending most of my time on, I mean, it's not a brain model, right? You have deep neural nets in there, which makes sense because they're doing so much amazing stuff now, right? But I mean, you also have an explicit probabilistic logic engine we call PLN. You have evolutionary learning that tries to, evolve computer programs by simulating the evolutionary process, and these are not things that explicitly occur in the human brain, although they have some analogy to some brain processes. The thing is, digital computers are not much like brains, right? So you have a digital computer that does logic of a sort natively on the chip very, very fast. Then it's very tempting to make an AGI system that does logic more natively than the human brain. But that said, I mean, it's really interesting to try to model and understand better and better how the human brain works, and there's sure to be new inspiration we can draw from better and better brain models, right? I mean, even if we're not trying to actually leverage these brain models directly to make AI systems. So what I've been thinking about in particular, I mean, it's some quite interesting mathematical mappings that seem to maybe have some practical import. So you can take an equation called the Bellman equation, or Hamilton-Jacobi-Bellman equation, and this equation, it basically governs how you make a series of decisions to get from your current state to some goal state that you want, right? This underlies an algorithm called dynamic programming, and it underlies, in essence, reinforcement learning, RL, which is a big part of modern AI, right? And a big part of modern LLMs even. Like, a lot of the reason DeepSeek was able to do training so much more cheaply than previous LLMs, I mean, that was because of use of reinforcement learning to a greater extent than other LLM training regimes had done before that, right? And reinforcement learning is really just an approximation of dynamic programming, which is governed by this equation, the Hamilton-Jacobi-Bellman equation, right? I mean, I'm simplifying some things, but one very interesting thing is that the HJB equation, in a way, is equivalent to something called the Navier-Stokes equation, which is the equation governing incompressible fluids, like the flow of fluid in the ocean or in your bathtub, or the flow of the air, which is considered a fluid, right? And what it turns out is that the space of smooth, volume-preserving mappings of a fluid, as that fluid evolves by Navier-Stokes equation, the space of smooth mappings evolves by, in essence, HJB equation, right? So optimal control is a different way of looking at fluid flow, which is cool, right? On the other hand, this HJB equation, optimal control equation, like, it also, if you complexify the variables in a certain way, map them from real numbers to complex numbers, right? It's also the same as the Schrödinger equation, which is like the basic dynamical equation of quantum mechanics, at least one of the key forms there, right? So these sorts of mappings are subtle and there's a lot of details I'm jumping past here, but they're very, very interesting. And I started to think, okay, well, the brain, in a way, is a fluid. There's a lot of stuff squishing around in there, right? And there's electricity moving around, which is fluid-like, though not exactly a fluid. And in the end, we can model what's happening in the brain as a sort of fluidic neural network. It's like a flowing around of attention using fluid dynamics equations. And it's a different way of looking at reinforcement learning or optimal control. And it turns out to be quite interesting. Like in fluid dynamics, there's something called the Reynolds number. And roughly, you jack up the Reynolds number, things get more turbulent. You decrease the Reynolds number, things are smoother, right? Well, in the mapping from optimal control and decision to fluid dynamics, more turbulence on the fluid level means more exploration, more imagination on the control and reinforcement level. More laminar flow, less turbulence on the fluid level. That corresponds to more exploitation of what you already know on the control theory level, right? So there's quite interesting correspondences here, and I realized you could model the brain as a sort of attentional fluid with attention and energy flowing around from one place to another by actual fluid dynamics equations. And on the one hand, it's just a different way of looking at control theory. On the other hand, if you want to go beyond just neuron spiking and look at, say, the slow wave of the Hodgkin-Huxley neuromodeling equation, which is flowing charge between neurons all the time, even when they're not firing. If you want to look at astrocytes and glia, other cells in the brain besides neurons, if you want to look at what's going on in like the water macromolecules floating around there in between the cells, all this is fit very well into a sort of neurofluid model of the brain. Now, I also started to think, okay, what about this Schrödinger mapping? Like, suppose there is some macroscopic quantum dynamic going on in the brain. Like, I don't buy Penrose, Hameroff, Orcho R and these theories that say all the thinking of the brain is happening at the quantum level in the microtubules or something like that. That seems highly implausible to me and sort of to contradict a bunch of known neuroscience. But I mean, there's a bunch of other more plausible mechanisms by which you could have some level of macroscopic quantum resonance across the brain. I mean, Matt Fisher's hypothesis of non-local correlations between the spins of phosphate atoms connected with phosphorylation of neurons, like that's one of multiple hypotheses that could plausibly explain some non-local quantum dynamics in the brain. So suppose you have some sort of quantum network happening in the brain, sort of overlaid on the neuronal network, participating in its dynamics, right? Well, then you can map this quantum network into the reinforcement learning control theory network via the mapping of Schrödinger equation into HJB equation, right? And then the funky thing I realized is that these levels can synergize. Like the classical neurofluid flow can have a sort of morphic relationship. It can synergize and flow along the same patterns as the macroscopic quantum network, right? Because these are all just, in a way, they're all just mapped into control and decision. So this sort of thinking, I mean, it's a bit out there, and of course these are equations and ideas. I think they're plausible, but there will be a lot of experimental work and more theoretical work to validate that these ideas really make sense and describe reality. But it's interesting how much room there is to explore, right? Because the deep neural net models that are driving so much of AI today, they're really very crude approximations of a very limited subset of what the human brain is is doing. Now, what is there to learn from AI about all this? Well, that's another question, but I think the answer is probably quite a lot. And as one example, I've done some math suggesting that in some ways a very complex system that's classical in a physics sense, like you wouldn't normally describe using quantum mechanics, say a big Hyperon system implemented across a bunch of ordinary computers, right? You can make some math arguments that a sufficiently complex classical system should be modeled using quantum math by an observer who's smaller than it. So like if I'm looking at a huge Hyperon system, a big computer network, because my brain in a way is smaller than the used Hyperon system, right? Then I should model this huge Hyperon system as if its internal states were quantum states. Now, what's even more interesting is if you have a small part of a big complex digital classical system like a Hyperon network, right? A small part of that system, like say the deliberative self-modeling portion of the system, then this small part of the big system should model the big system as if its states were quantum. And what that means is that a complex digital AI system like Hyperon, at the meta level, should perhaps be modeling itself as a quantum system, right? Now, I wrote a paper a few months ago looking at how to do attention allocation of resources within a Hyperon system, using a fluid flow approach, using this mapping between control theory equations and fluid flow, Navier-Stokes equations, right? So you could have, like, within a purely digital computer program like Hyperon, you can have attention flow governed by fluid flow, and then you can have self-modeling using quantum algebra, because that can be the best way for a small part of a big system to model the states of the big system. So then this funky model of the brain as a neurofluid, synergizing and harmonizing with a quantum coherent network, this actually becomes something that describes how a Hyperon system works, right? So we can see, even though we're not trying to emulate the brain or make a simulated brain in Hyperon, because we want to make better use of the affordances provided by computer chips that are doing native precise logic at the chip level, right? Even though we're not trying to build an artificial brain per se, many of these higher level dynamics and mappings that seem to be there in the brain may also be there realized in a Hyperon system in a different way, right? And all this is very exciting to me to think about, and it's also perplexing to me that so little of the AI field is even trying to go in this sort of direction, because what we've done is take a very crude model of a few aspects of the brain, deep neural nets, and then, bang on them to make them very effective practical systems for doing things. But there's a lot more inspiration to draw from all the rest of brain dynamics that the very crude, deep neural net model leaves out. So, on the one hand, I'm psyched about Hyperon, and I'm intrigued that these sort of system theory models of brain dynamics might help tell us something about how Hyperon systems should work. But I'm also sort of hoping more people can, open up their minds and try to understand all the aspects of what the brain is doing that current deep neural models don't even try to capture, and think about how these can be worked into all different sorts of AI systems. So I'm hoping to start up some conversation about this actually in a few months at the AGI conference that we're having in San Francisco in late July.